Hello everybody, my name is Benjamin and today we're going to be revisiting making these topographic map tags, but today is going to be much more of a tutorial, so more details and you should be able to follow along if you'd like. So let's get started. Here we are in Google Maps and we're just going to pick Antelope Island for today. It's here in the Great Salt Lake. I'm just going to pick a point and copy that. Then we're going to take that, the point 1 in the center of our map, and we're going to bring it into this script here. So this is just a Python script that you can run inside of QGIS. And what we're going to do is we're just going to paste it in this line. Right here, what we're doing is we're transforming from this coordinate system to this other coordinate system. Coordinate system that I'm using here is EPSG 3857, which is pseudo Mercator. Units are in meters, and it's a pretty standard map that you'd see anywhere. So I'm just going to leave that as is. This transformation not only changes what units we're inputting our position in from latitude, longitude to the meters that this map projection uses, but it also will transform all of the elevations to meters as well. These variables here are the latitude and longitude. We're just setting them to be 10,000 meters, again, same units as the projection, and 40,000 meters. We're going to take these radius values and we're going to add and subtract them from our original coordinate right here, and that will give us 4 unique corner points for us to make the rectangle with using another QGIS function, which is a min-max on the x and y. We're going to make a polygon out of that and then add that into our map here as a layer. So let's run that, and you see it shows up as this nice tan rectangle. And it looks like it covers the area we would like. Since this is over top of a lake, and I would like to demonstrate one of the transformations we can do in just the standard tag like this, all of the water is at sea level, and so we can just automatically call that out as the base of the map. However, on a map like this, or the one on screen, elevation of everything is significantly above sea level, and so we'd have to either add a second blue layer to highlight the lakes, or, as we're going to do here, we're going to actually cut the lakes out so that it's not as accurate for elevation, but it makes it so that we can have the lakes at sea level, so they're blue and they stand out a little bit more clearly. We're going to have to do a 2-step process to get the map cut to the perimeter of the island and not just all of it. So what we're going to do is use the vector geoprocessing and do clip. The input is going to be the Utah Major Lakes. The overlay is going to be Antelope Island, because what we're trying to do is cut out only the areas of the maps layer that shows up on our tag. We're going to set invalid feature filtering to do not filter. This makes it so there are fewer errors and it runs and completes properly. Okay, so there we go. We've only got the lakes and bodies of water that are on our map. Now that we have that, you can see that's that shape. What we can do is another vector option, vector symmetrical difference. And now we can select, need to rename this, clip Salt Lake, symmetrical difference. The input layer is this clipped Salt Lake, this purple area. overlay layer, we want it to be Antelope Island. We want this one, again, using do not filter, so that it has no errors that will cause it to stop. All right, there we go. So there we have just the region of land inside this rectangle. All of the water is now outside of that, and we still have the tan for the actual boundary of the map. We're going to be making two maps with this, one with the water at its proper elevation and the other at sea level. Next, we can use the Open Topography DEM downloader, and this uses an API key that you have to go and sign up with Open Topography to get access to. And then we're going to define the extent from a layer, and we're just going to select that. This will get us all of the vertical elevation data for the region in question. So this is all of the data we need to make just a standard rectangular tag with no cutouts, and this is ready to go. But we're going to take one more step and do a raster extraction, clip by mask layer. I'm going to select this one. I have to rename it real quick. Just renaming that so we can find it. And then clip by mask layer. Oh, that's already selected mask layer. Just have to find symmetrical difference. It's that one. All of these other parameters we can just leave as default and run that. So now if we just show that, we've only got the elevation data for the land masses, at least the proper terrain itself above the lake. So nice. So one thing I'm going to do before we export these to STL files is I'm going to add an offset to the elevation on each of these maps. The reason for that is maps like this one with Florida, the elevation difference between the land and the sea is nearly zero, and so maps like this would be hard to see because of that lack of difference. So I'm going to add 500 meters vertically to all of the terrain. I don't have to do that for these since we're a long ways away from the sea, and you can see the lowest elevation is 1,272 meters. So that's not going to help this map, but it's going to make it so that if I'm comparing something like Florida side by side with Utah, when I line them up, they're going to be in the same scale, same offsets, and you can actually one-to-one comparison, like those ones this much higher. Not that important as far as the way a tag looks, but it's going to make it so that it's a bit more accurate, and I like accuracy. So what we're going to do is this Antelope Island raster. We're just going to do raster calculator, and this clipped mask Antelope Island. Going to click that. We're going to add 500. And there's been a problem I've run into where if you're making on-the-fly raster, it will not save correctly. So, I don't know why, but it's apparently a bug in the system. So I'm just going to OK that. So we can have that, and then I'm going to do it again for this one, plus 500. Okay, great. So now we've got these two maps. They've been offset. Now we can export these using the DEM to 3D printing plugin. You just do that. I'm also going to be importing settings. This should give us the correct width and height and everything, and scale. So I'm just going to copy this and then change the island layer to be the one we're actually selecting. Repaste that, 0.0, and the height to be 0.32 millimeters. All these variables just define the size of our map. And this is the land only. Great. Export to STL. And then here, land only. Yes. All right, now that we've finished exporting both of those maps, we can move over to Blender. As you can see here, this is just placeholder, geometry, and the frame piece. There's actually a reason for having two pieces here. By using two separate pieces, I can print these, just the frame, as a standard part. And I can use a material such as PETG, which doesn't have as clean of print quality, but is more durable. And since this is what you're actually going to be hanging on your keys, that could be desirable. You can also use a thicker layer resolution, so maybe it's not a big deal with resolutions I've been printing here, where they're 0.16 and they don't take that long. But if you wanted to go to even higher detail, it's going to take a lot longer to print every single piece in that. So printing these at a relatively thick layer height, as well as out of more durable plastic, has some benefits. It also makes it so I can have some contrast here, as you can see. Tan and black. It shows up nicely. The other reason is this is entirely defined by geometry nodes, and we're going to go through the node tree that I've developed to make these. Alright, so this frame is not built with geometry nodes. It's actually modeled with modifiers and some direct modeling. So I just want to go through how that's done. I've got a collection right here called Tag Frame Construction. If we turn that on, see a lot of extra geometry shows up. The way I'm doing this is I'm actually starting off with a basic rectangle, and I've got this vertex group, just the corners. So I can come in here and make a bevel on just that vertex group that does those corners, giving us these nice rounds in a parametric fashion, so we can change that later if we need. And then I have another bevel that does not have any vertex group assigned, so it just does all of these corners just based on angles. And then I go in and start cutting out the booleans. So we've got this tag inner cut out, and it's this object. This one is using another geometry nodes tool. Nice and simple. It's another instance of this rounded rectangle that we used on the actual maps themselves. It's also using a taper, taper geometry function. So again, just selecting Z position higher than 0 and scaling it. That way we have, and we're using this group here, that way we have consistent angles on both the map and the frame so that they'll fit together. And then we're just transforming that geometry so that it's in its proper position. So a little bit of geometry nodes in there, as well as a bevel. This bevel's actually turned off, so I'm going to just delete it. So this is just, again, a rectangle, but I'm not using any of this geometry. I'm just defining this entirely with geometry nodes. Back to the main object. The next thing is we cut it out with this cube. This here is just a simple flat for the keychain to connect to and ramp up to the sidewalls that hold the tag in. Obviously it's helpful to name these, but I often just leave them as is and rely on the names of the objects to be descriptive. So this one is just cutting out the hole for the keychain, and it's just got one bevel. You can see right on that corner, right here. The rest of this is directly modeled. Next, we have the coordinate hole cutout, and so it's these objects that are cutting out the holes to see the coordinates. Again, another bevel, but they're just rectangles, beveled so that they cut out these nice slots. Next one is the name cutout, so you have named these modifiers so I know what they are. Cuts this section out. Again, just bevels. And then finally I've got this union with this detent object. And these detents are just icospheres that have been offset. So we start with the detents here. I've got a few different objects. Yes, so we start with the detents and then we add the detents with clearance. So I'm just using a displace modifier with the strength set to 1,000th. This means that it has a uniform displacement or scaling over every point of 1,000th of its size. So it's generally a pretty good way to get tolerances in objects, and I'm just using that here to make sure that the detents have enough clearance to snap fit in, but not to try and press fit and bulge the sides of the frame out. So nice little thing, and because they're based on the same core geometry of the detents, if I modify this, the detent clearance will update, and that is the object that I would be cutting out of the mating features. Now I've modified this a little bit to be simpler for the map side, and so it's actually using a geometry node's representation of these, which I mentioned briefly. But that would be the way I would approach this, is just offsetting the original object with the displace modifier. That way the geometry defining the cut as well as the detent bump itself are the same. So that's everything for this frame. This is what we're making with this modifier. Quite a few nodes. There is a method to this madness. Let's start with base bounding box. So this is relatively straightforward. We're taking the radius we want on the corners, and the x and the y and the z, and we're making a rectangle. So this is the shape we're making. The way we're making that is we're taking the x and y and the z and subtracting the diameter, so 2 times the radius, from that, making a grid out of those points. Then we're instancing a cylinder with the radius and the height from our inputs on those points. So we can see what that looks like. So we've got 4 cylinders, 1 on each corner, inset so that the outside width and length of them, you can see here, 0.97, 0.37, line up with these values. Obviously they're, let's see, 0.9, 0.36, or 3.6. These numbers are scaled later, but for now, you can see those numbers come out to the overall dimensions of this assembly. and then we realize instances, and that just treats every instance as part of the whole rather than part of individual objects. So that when we do the convex hull, it's just shrink wrapping the entire collection of instances as one object. So we get a rectangle with rounded corners. So I've made that as a grouped node, and then I'm going to put that into another group, which, see, tapers it. This one, all it's doing is it's selecting vertices by the position. Right here, it's anything with a z position greater than 0, and it's scaling it along the x, or along the y, and along the x by 2 different scale factors. That makes it so that the width and the length are more even, and we can look at that. The offsets are more consistent rather than being squashed in the y-axis. We have a smaller, different scale, we have different scales so that they offset an appropriate amount, and the slope on the sides is consistent. That's the main goal here. So this whole group here just makes this. We're using this transform here to offset it by half of the width and the length so that it ends up at the corner. So you can see we're just moving it over. And then we're scaling elements along the x-axis, and all that does is it makes it so that the taper is just a little bit narrower. That's going to be important later on when we're trying to fit it into the frame, so that there's a little bit of a tolerance and it's not size to size. It should slide better. The next piece is this corner cut, and we can just look at that. It's kind of a skewed rectangle or cube. This is a funky shape because we're not actually dealing with the majority of this shape. We're actually dealing with the Boolean cut that it performs on this corner. So you can see it's just this shape cutting the corner. The way this is done is it's a cube, and then we're applying a transform primarily by skewing it using this matrix transformation. So if you move it in the proper, if you adjust it in the proper values, it will scale it. And if you put it in values in other inputs, it will skew it along different axes. We're also then combining that with a translation so that we get it offset to the proper dimensions so it'll line up later with the rest of the tag. So that is the base bounding box geometry. So everything else should fit inside of this when we're all said and done. Next, I'd like to talk about these nodes here for putting the text on the bottom of the map. These three are pretty much the same with minor variations. They're using a string to curves modifier, and then resampling so that when we fill this curve, it's going to be a little bit less geometry to have to deal with. You can see it's just changing the density. Some of these have very few vertices, some of them have a lot, and resampling makes it more even. And then we are extruding this mesh, and you can see it just extrudes the outside and face that it extrudes to, but it does not include the original face. So what we have to do is then join that, realize instances, and merge by distance. That way these are solid manifold shapes that we can then use for Boolean operations later. And then we just transform it over to its actual resting position. You see there's this offset here. That comes back from this value, just setting the depth of the text. We also have the curve resolution here too. We also have settings specifically for the coordinates, setting the decimal precision and the text height. These values just go in there and into the value to string, because we're putting in the latitude and longitude as float values, not as text. This way we can change the number of decimal points after the fact. So that goes in, and again we're using string to curves, resampling, filling the curves, extruding. We're using separate offsets for the Y position, because as you can guess, we are needing to put the latitude and the longitude in different locations. So those are individual offsets, but otherwise they're using the same x-axis offset and depth offset. And then again, they're rotated and put into place here. Next, there are a few operations which we have to perform on the map itself. The first is we're bringing in this base height over text. This is just a slight offset. You can see it's 0 here. One of the options is to have sea level higher than the base of the letters that are cut into the bottom. This is where we can change that. Currently, I'm just using it as a 0 placeholder because I want the layers here that turn the back of the text blue to be the exact same layers that go on the top surface, but we can change that and give it a little bit more gap and more thickness if we would like right there. But we can also see here, this is a base plate. This is just a thickness here, the X and Y, 1 inch by 4 inches. It's a cube, and then again we're offsetting it to have the origin here at 0, 0. We also are moving the map itself up a little bit. The exact amount is just the height of this base layer, so we can look at it from the side and look at that. So see, there's this gap here. This gap here is only for the text. That is essentially the thickness of the engraving, if you call it that, of the text on the bottom. So we just offset it by that much so that when we're trying to cut the letters out of the bottom of the map, we're not cutting them out of the map data from QGIS. It's just really dense, and that would end up taking a lot longer. So we're doing a proxy step where we're cutting the text out of the base layer and then connecting the base layer to the bottom of the map later. And one other operation, this right here, we're just rotating and offsetting the geometry. It doesn't look very clear from this, but what we're doing, I just want to bevel this. I'm just going to bevel these vertices so you can see. Right here we are just rotating it 180 and offsetting it so that it's right on the corner. That's all we're doing here. And then next we move into the Booleans here. So here what we're doing is we're cutting this base plate to fit inside the base bounding box. That way when we join it back to the map, it will be the correct size. And then we go through and cut out each of the text units. Next, I want to show you these detents. These are just the spheres, so that when these come together, it clicks into place. These spheres are detents on the bottom of the map. It makes it so that when you're putting these two together, they click into place and hold it nicely. We're just having, again, another grid with the size defined, and then we are instancing spheres on those points, and that's what you can see here. So just instanced spheres placed at those points, and then we're doing two separate Boolean operations. One is cutting the detents out of the base plate, and the other is cutting the detents out of the actual map geometry. Doing two separate operations because at this point these two meshes, the base and the map, are still separate objects, and that way they each cut out properly. And then final step is unifying them into one object that we can then print. So that's kind of the overview of how this node tree works. The reason for using nodes in the first place is so that all of this work can be upfront, and then anytime I want to make a new map, all I have to do is apply this modifier and set 3 values, and the map is already done, cut to size, and I know that it will fit inside one of these frames without any hassling, any checking, measuring, any of that. So geometry nodes is a lot of work up front, but in theory it pays itself off if you ever do it again. Next we're going to be importing these STL files. You just can select these, set the scale to 0.001. That just compensates for the Blender units being different than the default units in the STL file. And there we go. We import them and we've got geometry. And we can just move these over. And you can see the difference of cutting out the land all the way down to sea level is pretty noticeable here compared to our normal map. Obviously, this isn't the most drastic. Obviously, here in Utah, we don't need this kind of offsets, but I wanted to show how this works, or could work, if you're wanting to make really simple and easy to manage water lines in a map. But what we can do now is we can select our coordinates from QGIS. Just gonna select that. I'm gonna come back over to Blender. I'm gonna add the modifier. I'm going to select map to tag insert. And I'm going to turn off the real-time display so that I can set these values without it crashing. And there we go. And this is Antelope Island. Alrighty. What I next want to do is I want to apply the scale, because we brought it in at a scale of 0.001. So right now you can see its scale is still at that. So Control A and scale. That way, when this modifier is applied, it's at the correct scale. Turn that on, and it'll process it and apply every single one of those nodes and give us a printable map. Alrighty, that looks like something. Neato. You can even see the causeway right there. Looks kind of screwy though. Well, we can do the exact same thing with this one. We're going to add jump node, insert, scale, copy this, and then open that. Nice. So you can see the island is pretty flat to the water, which I'm going to show next in Bambu Studio. That might be a little bit of an issue, but we're gonna demonstrate both of these so you can see what they look like. But before that, we're going to just have to export both of these as STLs. The scale, I have to go back, be 1000. And selection only, that's important, especially with large files. We can do the same with the other. But that's all of the steps here in Blender. Here we've got our Bambu Studio open, and we're going to just bring in our STLs that we exported from Blender. We're not going to have these as a single object. And then just arrange. So there we go. We've got two maps. Nice and easy. And what you can see here, when we slice this, even at the 0.16 millimeter, the one here on the left is not very detailed. We're losing some of these low-level coastlines and even a whole section down here by Salt Lake, just because Salt Lake is really flat, and this is one of the times where it does benefit to add some differentiation between the water and the land, just visually. And going down to sea level is maybe a little bit extreme, but it kind of illustrates the differences that we're going to be making it more valuable sometimes to modify the map from true data standpoint. So one thing we're going to do to start with is just change the filaments here to just a blue layer. Delete that. Change it back to tan, and we can see it just makes it so that we've got water and the text on the bottom is now blue and not tan. So I printed a map earlier where I did not do that. I just had it tan all the way through. It was hard to read, and that's trying to double duty the color change. So doesn't that look nice with the coastline there? I know it's not accurate to the way it's actually. It's flat, but looks nice. So I can hear what you're saying. One thing we could do is come and add another layer that just changes the water level for the standard map, and we can do that. So arrange that, and let's slice this, and we're still going to change layers 5 and 6 to blue, but we're also going to change layers 16 and 17 to blue. I think that's going to be correct. Let's just see. Nope. Need one more. Oh. Yep. Slice that. Alrighty. So this is another way to do it. It's obviously a different type of visualization of the same data. You can see it is different what it's showing, but that's just another way of processing the same data. So now that these are ready to go, let's throw them on the printer and see how they turn out. If you've made it this far in the video, I just want to say thank you for watching. When I was originally planning to get this video posted, I was going to say something about thanks for 100 subscribers. And you guys blew that way out of the water. Just want to say I'm going to keep on making stuff. Planning to post these files for the maps on Patreon if you want to download them. The Blender files, the STL files, as well as the QGIS Python scripts. So if you want to download those, you can go check them out on my Patreon, which I'll have linked down below. Otherwise, I'm thrilled to do this kind of stuff, and if you guys are thrilled to watch, let's keep on doing this. So, till next time, catch you later.